Hello, everybody. It's my pleasure and honor to give a talk in this WSTA 2022 web conference. I am really sorry that I cannot actually be there in Kerala in person to attend this conference, as I am sure all of you are. All of us would have liked to attend this conference in person. Um, Also, I do apologize for recording this video ahead of time. I have a very unstable internet connection in the last couple of days, and I'm not quite certain I'll be able to join in on time. And then, even if I join in, I may not be able to do a live presentation. I'm actually doing this presentation separately. Then I'll go somewhere else uh, and send it by email to the organizers. Speaking of which, again, my heartfelt thanks for to Professor Satish Kumar and other organizers for uh, giving me this platform to talk to you. And so let me start this recording. Let me start the actual technical talk. And speaking of technical talk, well, I will actually avoid a lot of technicalities in this talk, but let me start by sharing my screen. So what I will talk about today is on simultaneous selection of multiple variables. That's really the primary topic that I'll talk about. And then there's an application actually in the talk title and in what you see for the as the abstract of my talk on the conference website. We talked about this selection of important single nucleotide polymorphisms, the so-called SNPs, SNPs, in familial genome-wide association studies data. But when I was writing on these slides, we have many applications of this multiple variable selection, and so I decided to add at least another one, that on Indian monsoons, selection of variables for study for understanding of Indian monsoons. I'm sure both GWA's studies as well as monsoons are terribly important, terribly relevant to the audience. Um, Several members of the audience, I'm sure, are specialists in either one or maybe both of these topics. So, what am I talking about here? Before even getting there, let me just acknowledge that this is joint work with Dr. Shubhabrata Majumdar, Shubho. So Shubho Majumdar graduated, so he was my PhD student about 4 or 5 years back. After graduating from Minnesota, he was a postdoc with Professor George Michaelides in University of Florida. Then he was in AT&T Research, the team, the research team of AT&T, Bell Laboratories, and so on. And very recently, he moved over to a new job at Splunk, which is a startup company. So Shubho is not just a collaborator in this research. Many of these ideas have been inspired by Shubho, and actually he came up with several of the concepts that we'll talk about. So this is very much of a collaborative work. All right. Also, this what the topic of this talk. I understand. Things are rushed in conferences, and I never understand what's happening in a 20-minute, 25-minute, or even a 1 hour long talk. So it's better to start with giving references. So this particular talk is based on two papers. This particular paper, feature selection using e-values, this is a one by Shubho and me. This just got accepted in the International Conference of Machine Learning, so ICML. So this conference is the topmost conference on machine learning. It's the computer science, the machine learning version of, what would be analysis of statistics. So it just got accepted for that. So part of my talk is based on this particular paper. Here you have a link to the archive version of this paper, and you'll also find the details of this work in ICML proceedings once it gets published. It's been accepted. It will take a few more months for the actual publication to come through. And the second part, also joint work with Shubho and two other colleagues of mine at the University of Minnesota, Professor Sauli Basu and Professor Matt McHugh. This is based on essentially using the eValues mechanism, and I'll talk in a minute about what do I mean by the eValues mechanism. So on using the eValues mechanism for a familial GWAS study. So this paper is just about to be submitted. So it is under revision, and we have completed the revision, and I think it's going to be submitted this week, next week, something like that. Also, a preprint version of this is again available on archive. If you wish to follow up on these talks, of course, you're more than welcome to contact me. And of course, you can look up both of these papers. All right. So let me tell you what's new here. What have we got here? In essence, we have got a new model selection technique, or a variable selection technique, or a feature selection technique, whatever you call it. So it's a new model selection technique. I'm not being cagey about whether it's a model or a variable. The principle is very broad. The principle of using eValues. eValues is a short form for evaluation maps. Is very broad. It applies to all kinds of selection of statistical models, basically, or machine learning models. So you might be wondering, why is there a paper in the topmost conference in machine learning on model selection now? There's so many of these techniques around. There is the Akaike information criterion, the Bayesian information criterion. There's a bunch of other things like Mallow's CP criterion, and these days you've got even more interesting variants, like, for example, a lasso or any of this penalized methodology can also do model selection as part of what it does. So why do we need a new method? So what the eValues mechanism for selecting model does is that it has got three very interesting properties. First of all, we fit just one model. All right, essentially the largest model that we can find in the version that I'll present on today, in what's given in the slides to come. We fit just one model, and then we just keep dropping one coefficient after another and then evaluating. Does that dropping of a coefficient, so replace a coefficient with 0, is that a meaningful thing to do or not a meaningful thing to do? So this is very much like what you learn and you teach in class. For example, while teaching linear regression, it's not identical, but it follows along similar lines. So you fit a linear regression, you have coefficients, beta 1, beta 2, beta 3, beta 4, and so on. And you get your estimates, beta 1 hat, beta 2 hat, beta 3 hat, and so on. And then you do a test. Is beta 3 equal to 0? That's where your t-test comes in. Do you want to test if the entire beta vector might actually be equal to 0? That's where your f-test comes in. You can test for contrasts. You can test for linear combinations of beta. Is beta 5 equal to beta 7? In which case you again have one dimension reduced for the parameter vector. There's beta 5, if it's equal to beta 7, you might as well plug the same number in both places, right? So that very classical methodology does not really have a model selection equivalent. So if you are fitting beta 1 through beta 5, and then you happen to test that a beta 5 is actually equal to 0. So let's say you cannot reject that hypothesis. You accept that beta 5 is might actually be equal to 0. You accept that null hypothesis. Does this mean that that particular model, now you can go ahead and move with beta 1, beta 2, beta 3, and beta 4 only? No, you cannot. It requires you to retroactively fit that model. And you cannot even fit it to the same data set, because then you're data snooping, then you're really cheating, because you fitted with the 5 coefficients first, then you drop the 5th one, and then you retroactively selected the top 4, and then you get to a region where it's neither ethical nor theoretically correct. So you tend to get super efficient estimators and so on. So what the evalues mechanism does in very broad terms is that makes that a valid method to do. It's not just about dropping a coefficient. There are other steps, of course, but this evalues mechanism allows you to fit this model with beta 1 through beta 5. Then just find out, can I drop beta 5? Does that, if I replace beta 5 with a 0, is that a valid thing to do? Well, the evalues methodology that I'm going to talk about, that does that. Then, of course, the data that we allow, it doesn't really have to be IID data. I mean, it can be dependent, it can be heteroscedastic, there can be a very complex model that we are using in order to fit the data. So the parameters as well as its evaluation methodologies can be very general. So parameters can be estimated using essentially any kind of an optimization. So whether it's maximizing a likelihood, maximizing something else, solving a set of equations, whatever have you, the evalues mechanism does that. So that's the advantage. There's computations involved, of course. There's actually 2 separate kinds of bootstraps that need to be done. And I shouldn't even call them bootstrap. They're more general resampling schemes that need to be implemented. But many of these computations can be done using parallel computations. So parallel computing. So the computation is actually much faster. And the other big deal is that in a typical model selection methodology like AIC or BIC, you are technically required to fit 2 to the power p number of models, where p is the dimension of the parameter. People don't do that, but that's what one is supposed to do. Evalues makes that instead of looking at 2 to the power p many models, so if you've got 5-dimensional coefficients, you should be looking at 32 models. It allows you to fit 1 model and then evaluate p more. So basically, look at just p plus 1 models. So that's very, very high level overview of what our mechanism is. So let's run through an example just to get this thing sorted out. Let's say we have observed data on a response y, and let's say 2 potential covariates, x1 and x2. So ith observation is yi for the response, xi1 and xi2 as the covariates. And let's say that the true model is this one, yi equal to 5 times xi1 plus ei, where ei, let's just assume it has got IID normal 0 sigma square noise. This is an example, of course. So basically, xi2 has no role to play. xi2 is irrelevant. So I can write this, of course, as 5 times xi1 plus 0 times xi2. And if I denote these coefficient values, now, of course, I don't know whether it's 5 and 0 or whatever. So let's denote them as beta 1 and beta 2. So beta 1's value happens to be 5, beta 2's value happens to be 0. That's our example. And then here's how the evaluation mechanism goes. We get an estimator. It could be your MLE from the Gauss Markov model that was there in the previous slide. It could be least squares, what have you. You can use a robust mechanism. You can use list trimmed squares for all you know. So any kind of a good estimation method for obtaining an estimator of beta that works. So let's call that beta hat. Now beta hat is of course a random variable, right? It has got its sampling distribution, and this sampling distribution is going to be useful. And you start the you can see the relation with Bootstrap sort of developing out here. So what we do is we basically evaluate the data depth, or I should really call the evaluation data depth is really a special case of an evaluation map of 3 vectors. First of all, I take my beta hat vector, the entire beta 1 hat, beta 2 hat, and I do an evaluation of that. Then I just drop beta 2 hat and replace that by 0. So then I use beta 1 hat and 0. Similarly, I just drop beta 1 hat. So I evaluate 0 and beta 2 hat. So I just evaluate these 3 maps. All right. I compute one estimator and then I evaluate these 3 maps. And I'll tell you what do I mean by evaluate these 3 maps. They're there in 1 or 2 slides. So if it turns out that the evaluation of this quantity, beta 1 hat 0, is less than that of beta 1 hat beta 2, then beta 2 is a valid variable to use. Beta 2 is a non-trivial, non-zero coefficient. Right? Similarly, if 0 beta 2's estimator evaluation happens to be less than that of beta 1 hat beta 2 hat, then beta 2 is a valid coefficient to use, and so on. So if you remember in the previous slide, we had the beta as 5, 0. So basically, what we should expect is that 0 beta 2 hat, the evaluation of that would be less than that of beta 1 hat beta 2 hat, but not beta 1 hat 0. So that the evaluation of that would not be less. And this is, so what does an evaluation map do? This is what evalus are all about. So this is with respect to data. So we've got beta 1 hat on this axis, beta 2 hat on this axis. And there are basically 4 models. Both beta 1 and beta 2 hat are non-zero. Beta 1 hat is non-zero, but beta 2 hat is 0. The other way around, one of them is 0, the other one is not 0, and then both are 0. So one of them is this dot here. Another one is that red line. Another one is the blue line, and the blue line is the correct, most parsimonious model. And then things on this beta 1 hat, beta 2 hat plane. Now remember, beta 2 is actually 0, but if you don't know that, if you pretend it's non-zero and work ahead with it, there's no harm done. So it's an adequate model. If you take both coefficients to be non-zero, there's absolutely no harm done. This is what drives modern artificial intelligence, artificial neural networks, deep learning, and so on. That there's no harm done if you over-parameterize. So what this evaluation map does is basically gets us a 3D surface on this beta 1, beta 2 plane. So if I think of beta 1 as the x-axis, beta 2 as the y-axis, an evaluation map is a function on it. It's basically on the z-axis, on the z-axis. It takes its highest value, it takes its peak at the correct model, 5, 0. That's where it takes its highest value. And then in sort of concentration ellipses around that, it just comes down from there. So when I estimate this, I will probably find a value out here or somewhere, beta 1 hat and beta 2 hat, So beta 2 hat is not going to be 0, even though beta 2 is 0. So this is basically the mechanism. I mean, the closer we are to the right value, this will be at the highest possible evaluation. So that's the mechanism. Let me go do away with the technicalities and shorten the talk a little bit for that purpose. So what an evaluation map does, what data depths also do, is that they are trying to do exactly what the previous figure was doing. Build a function that is like this, that takes its highest value at the correct combination. Some examples out here. Let's say your distribution that is governing everything is normal 0, 1. Then if you take 4 times phi of x, 1 minus phi of x, it maximizes itself at 1/2, at 0. So that, and there the probability is, so this evaluation happens to be equal to 1. The probability phi of x is 1/2. This is an example of an evaluation map. Let's get to, so data depths are just multivariate equivalents of these things. They can be applied to high dimensional analysis. And here's an example. Take a Mahalanobis distance. Let's say we're looking at a p-dimensional normal. So with mean theta, variance sigma, look at x minus theta transpose sigma inverse x minus theta. So that takes the value 0 at theta, and then it sort of uniformly goes down, right? I mean, that's this function. This is an evaluation map. So basically, data depths are special cases of this. Let me get to examples quickly, because I would otherwise run out of time. So here's my example for Indian monsoons. It's a very complex phenomena. I do not need to tell you. You are all, many of you are based in Kerala. You are experts in Indian monsoons just from experience from a long time. So there are a number of drivers of Indian monsoons. There's the air from Eastern Indian Ocean that comes in. There are air descending on the Arabian plateau. There's the Somalian jet. There's lots and lots of drivers to this, and this is just what the data has been collected from. And there are so the basic idea is that there are literally hundreds of variables that people study as potential predictors of Indian monsoons. Again, I do not need to tell you how critical it is to be able to predict when are monsoons going to start. Is it going to be a good season, a bad season? Is there going to be flooding, or is there going to be a drought, or are things going to be just about right? So among these thousands of variables that people do study, in the climate community and in the physics community, the related physics community, there's not a good idea about which variables are important and how important are they, and what sort of the ordering of the variables and so on. What you see out here is a list of the variables that we found using the e-values mechanism to be important. And a few of these, they have been known, papers in Nature and Science have been written on how important this is. So for example, this delta TT degree Celsius, that kind of a variable. Of course, latitude is important. Again, I don't need to tell you how important latitude is in terms of, or longitude is in terms of, when should monsoons onset, how strong or weak the monsoons are going to be at a given location, and so on. So one of the things that we could do is we could take every possible variable and look at what's happening, how good are we in terms of predicting. And we could take the reduced model that is selected using the e-values mechanism. And you can see here that the reduced model, first of all, has lower bias. This is the dashed line as opposed to the full model having solid lines. but it has a much lower mean squared error. And let me go to this map. So this is on a holdout sample, all right? And this black line is the truth. The reduced model essentially captures the truth. This is for the year 2012. Whereas the full model is biased. And there's nothing peculiar about 2012. It's just that we just plotted this up. A similar feature, similar properties are being shown for other years as well. So the whole idea is that this model, the e-values selected model, does a much better job of capturing monsoon patterns. Remember, this is a prediction map, so this is being used ahead of time. So I expect great things from our model there. Let me really quickly go over my other application, which was mentioned, the SNPs and GWA studies. So this is based on the Minnesota twin family study data, which is a very long longitudinal data. So it's been going on for decades now. I think it's 40, 50 years of data there, covering about 10,000 participants. So this data is about twins and their parents and so on, and their other brothers and sisters. But the primary objective is to study twins. Now there could be triplets and quadruplets and so on, and then these twins may have a younger sister or an older brother. So this whole family is studied together for several generations. And data is collected both on genetics, on phenotypical patterns, on behavioral patterns. Behavioral patterns do happen to be very important out here, because the main objective of study is the effect of genes and the effect of environment, the effect of gene-environment interactions on certain behavioral patterns. Do people tend to get addicted? Do people tend to have alcoholism? This sort of behavioral patterns. So in what I'm going to show you, this is about gene-environment interaction in relation to alcohol consumption patterns among teenagers. So 14, 15, 16-year-old kids. So when do they start becoming alcohol consumers, start drinking and then become alcoholics and so on? Remember, this is a very long study, going on for decades. So they do have data on this sort of stuff. To cut the story short, again, we have used the e-values mechanism. We've found out several interesting genes, and SNPs within genes. There's quite a lot of them that we found out. And these things, so we did some cross-validation studies. It turns out, if you look at this map, so this is for the first gene, GABRA2 gene, and here are the important SNPs. We seem to have got all the important SNPs, and we have managed to take out pretty much, marginal but still unimportant gene in this whole scheme of things. Same thing goes for a second gene. Here's a third gene, and so on. So I think I've been running out of time, so let me stop here by thanking the funders of these projects, so people who have partially supported this project, the United States National Science Foundation, basically, and I also have a grant from Cisco. And thank you very much. Thank you. I have probably overstepped my time, but I wanted to do this recording and make sure that we have something to present, something to show to you, just in case I'm not able to join on time on the internet and do a live presentation. Thank you very much. Feel free to send me emails with your questions, just in case I'm not there during the live presentation.